All right, find this limit. Approximate if necessary. Do you remember the way to prove this? On this one, our limit's going to infinity. On top we have the sine graph. On the bottom we have x. We know something about the sine graph. The sine graph, that's cosine. Sine graph is that wave that starts here. It goes like this, and we know it always stays between 1 and -1. So that top value is always going to be something between 1 and -1. Even as we go way out here towards infinity, it still stays between there. However, our bottom number, x, as we go to infinity, that's going to get very, 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 very large. And so my guess here is that this limit is going to end up being 0. In fact, if we look at this graph, you can see here that for sine of x over x, it's kind of this wave, but this wave keeps getting closer and closer to 0. So yes, it doesn't look like, in fact, we got it right. Do you remember the way to prove this? If you remember, there is a method called squeeze theorem that we're going to preview coming up in a later video. But squeeze theorem is the way you prove this. And the way you do it is to start with the fact that we know that sine x is always between 1 and -1. And then we want this to look like sine x over x, so let's divide all these by an x. And now also let's do the limit of all these. So if we do limit as we go to infinity of -1 over x, we do the limit as we go to infinity of sine x over x, and we get the limit as we go to infinity of 1 over x. Well, we don't know the middle one, but we know what these ones are. As we go to infinity, that's going to go to 0. On this right side, same thing. This is going to go to 0 as the limit goes to infinity of 1 over x. And so that, by squeeze theorem, forces this limit here to also have to be 0. All right, let's look at one other one here. Find the limit. Approximate if necessary. Do you know the way to prove this one? On here, as we go to infinity, e to some big number is going to be very large. X is also going to get very large. So what do we have here? Well, this is one of those where you got infinity over infinity. You could guess or approximate which one of these is going to get bigger faster. My guess is an exponent to a very large number is going to be bigger than the bottom one. So I think this is going to keep growing. We could look at the picture, the graph to tell us that. Here's the graph of e to the x over x. And yeah, you can see on this right side what's happening. This is increasing. So my guess is that this answer is going to actually end up being infinity for the answer. It's going to keep getting very large. How do we prove it? Do you remember? This is one, since we have infinity over infinity happening here, is a method called L'Hopital's rule. I'll kind of show you this because you have done it before, but we'll go back to it when we get back to derivatives. But it is limit, so we kind of have it in this one too. L'Hopital's, remember, you need some kind of thing like infinity over infinity or 0 over infinity. And what you do is you take the derivative of both top and bottom here. So let's indicate we're using L'Hopital's. And we take the derivative of the top and bottom. Derivative of the top would be e to the x. Derivative of the bottom is 1. So what's this going to equal as we go to infinity? Yeah, infinity. That's going to get very large as x gets very large.